Okay. So now the camera's also recording along with this. Doesn't matter, but now I'm going to switch the input so that you can see the paper. Input. So we're recording all kinds of stuff. The camera's recording my voice, the microphone's recording my voice. But essentially I have here a nice little piece of paper, and you can put here examples. So I'm going to be just working with you here. So this is my handwriting. That's a little freaky, but that's okay. And I'm just going to, let's just put here EG. All right? And the nice thing about doing a lesson this way is that you can see the way I'm developing it. If I were to just splash a picture up on the smartboard, you wouldn't see the way I would manipulate the protractor, and you wouldn't know how to do it. So let's start by just drawing a mirror, and I'm going to have the ray coming in like this, very straightforward. So I'm going to draw the mirror, just like that. And I'm going to put some marks on the back side to represent the fact that that's the dull side of the mirror. And we'll follow the instructions just as they're stated. Let's say I don't know where the ray is coming from yet. We'll do an example like that in a moment. And let's just pick a spot on there to be the point of incidence. And now I'm going to manipulate my protractor. And many of us the other day wanted to put our protractor like this, but that's not the way we do it. We want the normal to be perpendicular to it. Now, notice this little trick. In a protractor, you'll notice that there's a little bit of plastic that kind of sticks out the end, and the 0 is up here and the 180 is down there. But this plastic, we're going to assume, is straight and is also perpendicular to this 90. So technically we should, actually, maybe we'll do it the proper way. Put a mark up here. I could have just slid the protractor back and just used the edge of the protractor, but we'll do it properly. Notice I've got the dot at that kind of vertex right there, and I'm putting my mark up there. All right? And now I'm going to take the protractor as a straight edge, and I'm going to make a straight edge right there. See how I've now moved it like a ruler? No problem. And now I'm going to put the dashed line representing the normal. And you do not need to label the normal because we draw it the same way all the time. The normal's the dashed line, the mirror is the straight line. Let's take our ruler and let's just have a ray coming in. And I really don't care what angle you choose at this point. So just have a ray coming in and hit that point of incidence. Put an incoming arrow. Doesn't matter what angle. Wilson, if you're debating on which angle you'd like. You got a favorite angle? No, just put anyone.
Oh, I did.
Excellent. Taking the protractor. Again, we're always measuring from the normal. And now we're just reading an angle. Notice I'm starting on the 0. I'm not reading from the 180. So I got 10, 20, 30, 40, 50. It's looking like it's not quite to 2. So we could, oh yeah, no, it looks like 2. 1, 1, 2. So I would say for mine, it's 52.0 degrees. If it's halfway, you can put 52.5. Yours probably isn't 52. If it's not 52, don't write down 52. We got our number? Flip the protractor over to the other side. Get it on the 90. Get it on the 0. And measure out to 52. 1, 2. Put a little mark out there. Take it away. And again, you can use the straight edge of the protractor. And I'm having difficulty because I can't look down over the top because I've got various cameras in the way. Please label it as well, 52.0. Yep. No, it's okay because you've got 5 angles in there, right? So it gets pretty tight. I don't care. You can, if you did it, don't worry about it. And if you didn't, you can just put it on the table. All right? Yep. Yeah, please. Arrows on all the rays. One's coming in, arrow in, one's going out, arrow out, because they're very important. Okay, let's do another one here. And let's just change things up. Because on a test, I like to change things up. This time I'm going to put the mirror this way, So there I've got my markings like that. And this time, let's have the ray coming in before we even draw the normal, and let's have it coming from the top for no particular reason. So I'm just using the straight edge here. I'll use a ruler instead, but you could have used the straight edge, and I'm gonna just have it hit right there. No particular reason. So like I said, rules 2, 3, and 4 sometimes happen in different orders, because I could give you this picture, and there's a little assignment at the end that I ask you to do where I don't, give you the normal first. So in this case, we have to locate the normal. The point of incidence is defined as being that point where it hits, so we don't have to find it. So let's draw the normal first. You can draw it with the protractor either way, it doesn't matter, right? You could draw it with it that way, or you can draw it with it that way. Just because of, the way I'm working down this way, I'm gonna draw it this way. So again, I'm putting that 90 right on the line. I'm putting that guy on the dot. I'm marking my top end right there. I'm taking it out of the way, and I'm going to use the straight edge of the protractor to mark my normal. And again, I'm not working from the top, so you can see mine was shifted down a little bit. That was sad. I can't look straight down because of the position of the camera. You guys can get a little closer. Same thing now. Flip the protractor around, measure angle I, flip it around, measure angle R. It's not that exciting stuff, really. So here we've got angle I, always from the normal. And again, whatever your number is, because of the way I'm using the protractor, it's this outside set of numbers, 10, 20, 30, 40, it's looking like 42, 1, 2. Ooh, that's exciting. 42.0 degrees. Because you can estimate that little bit of a degree. And I'm going to flip it around. I'm going to locate the same one. I always find it interesting that when I ask students to just kind of put one in there, and I do the same thing, I always end up pretty close to 45, because you just kind of end up, you just go, oh, the middle, we'll put it in the middle. That's the way I always end up. So 42, put that on there, outcoming ray, bang, 42.0 degrees. All right? Okay? I'm not gonna do any more of these with you, but like on the sheet, I have some that are on an angle, where the mirror looks like this, and the ray could come in like this, right? And again, I'm just trying to mess you up. And you know what? When you're doing this as a little assignment or even on a test and I try to mess you up and you don't like it, turn the picture around so it looks like it does under normal conditions. Just turn the page over until you get it looking the way you want it to look. Put a normal on it, have the reflected ray, and you'll be just fine. Okay? All right? All right. So now the next thing I want to find, and I can switch back, I guess, to the PowerPoint. I wonder if my input button works. So the next thing I want to do, so here we've got the examples. And again, same stuff, right? Don't worry about it. Now we want to talk about how images are formed. So you can put here example ray diagrams for images in a plane mirror. Don't write that arrow down because I'm going to switch you back to my picture, to my camera here. And I'm going to draw that for you. Just going to see if this is still recording. End up with my battery dying on me or something crazy like that. So once you get the title down, I'm going to switch back. So don't worry about that arrow. Notice the last ones we did were just rays. We were just doing reflection. Now we're going to do a ray diagram for an image. And this is what you were looking at in the second experiment. How do we find that image? So I'm going to switch back the input. We got the title? We're good? Oh, it's not liking my input button right now. Oh, success. There we go. So for this, I want you to draw a mirror, and the mirror is going to be up and down, as if you're looking into the mirror. So somewhere in the middle of your page, and this can be fairly large, make a fairly large line. There's my top, there's my bottom right there, and I'm going to put the back of the mirror over here. All right, Those of you who are very picky about your pictures, you probably don't.
This one can't be close to the edge, can it?
Ah, this one can't be close to the edge, correct, because I'm gonna end up with an image on the back side. Very good. And notice how big my mirror is. It's almost as wide as the field of view there that you can see. And I better make sure I'm getting this on. I'm getting this on my picture. Yep. So now I want to put an object out in front of that thing, and I'm going to put an arrow, and that arrow is then going to go out here, and I want it to be kind of far enough out here, and I like to put it on an angle because then it shows you how we can have different distances, and I put the arrowhead there. So notice that my arrow is about half the length of my mirror because I'm going to have some rays bouncing off of it. So here's what we call the object. I'm going to just put a big O above it. And in the lab, you guys did object 1 and object 2. I'm just going to call it O, the object. And we want to find I, the image. Okay? So what happens when you look in a mirror is you look into the mirror at home before you get to go to school, and light from the lamps that are usually above the mirror or from the side strike your face, and then all kinds of rays come off of your face. So if you imagine this as being your face, then there's all kinds of rays coming off of this object heading in all directions. But all the rays, to analyze them, are way too complicated. So we only want to analyze, well, how many rays does it take to find something in an optical thing? Two. We needed 2 to find the shadows. We need 2 to find an image. So we're going to take 2 rays that come off of this. And it doesn't matter which 2 rays. So I'm going to just have a ray that heads up, just because. And I'm going to have that ray go, and I'm going to have it hit the mirror. Now we have to do exactly what we did in the last exercise. We need to draw a normal, measure the angle of incidence, flip the protractor around, measure the angle of reflection, and draw it. All right? So we just have to get down to business at this point. I put it on there. You guys can just go ahead. I mark right there. I draw my normal. I put the protractor on there, slide it back essentially. Mine reads 25, but it looks like it's past. Slightly past 25. Ooh, that's evil. 25.1? Goodness. 25.1, 25.2 degrees. Doesn't matter. You write down whatever your number is. I'm flipping it over. I don't like this ruler. Why doesn't it have like longer lines for the 5? That's terrible. 1, 2, 3, 4, 5 and a bit. And then the ray is going to come out. Now, we've already done an activity, and we already have an idea on what we need to do in order to locate the image. What did we have to do with some of the rays in order to locate the image? Anybody remember back to Friday? Long time ago. What do we have to do? Yep. Extend the reflected rays behind. So let's go ahead and do that. I'm going to use the longer ruler here. I'm going to put it right on the line there, if I can get it right. And I'm going to extend it behind with a dashed line. Now I need a second ray. And here's where I use my brain so I don't have to work so hard. What's going to happen to a ray that comes right down straight 90 degrees from that arrowhead to the mirror? what happens to that ray, Shane? It comes straight back. Now that saves us an awful lot of work to do. Here's why, let me show you. So, if I put that right on 90, and now notice I'm using the protractor now as a flat edge. And it is, the protractors are built that way. If I put it right on 90 and right on the arrowhead, this ray is going to, I gotta move it up a little bit. This ray is gonna come in, it's gonna hit the mirror, and then what's it gonna do? Come right back. So where do I extend my ray? Straight in behind. And that is the best little cheat move. You got to arrow in, arrow out. And where our eyes perceive the meeting of the rays, we have our arrowhead. Now let's talk a little bit about the way our brains work. Our brains are excellent at following rays of light back to where they spread out from. So when a ray of light comes and hits you in the face, that light, so the light here, so from here, it hits you in the face, and then the rays spread out, say from the tip of your nose. And when I look out there and I look at the tips of your nose, which is a little weird, I guess, the reason my brain can locate your nose is because it's very good at following the rays back to the point of origin. But our brains are good at doing that, but they're not very smart. So when you look in a mirror, your brains see rays coming out from the mirror. And again, our brains are good at following those rays back to the point where they appear to come from. When our brains kind of find that location on where it appears to come from, we see something, we see a thing. But in this case, we were tricked. We see an image, we don't see an object. We see where light appears to be coming from. All right? Let's do the same for the bottom side of the arrow. Doesn't matter, we could have a ray going up, but I like to put the ray down just to kind of keep it not too, kind of, I don't know, bunched up. I don't like too many rays in one spot. So we're doing the same thing. Drawing a normal. Measuring an angle eye. It's looking like I've got 22. And I know I'm going to have to extend. And now I'm going to use the most awesome ray there is, because it saves us a lot of time and effort. It's going to hit, it's going to come back, I extend in behind, and I have located the bottom of the arrow. And we could do the same thing for each point on the arrow. We could do 2 rays for here, and 2 rays for here, and 2 rays for here, and 2 rays. Really get annoying, wouldn't it? So when we find the extremes of the arrow, we say to ourselves, good enough. It's a linear thing. We connect it, and we got it. That doesn't look too bad. Now, if we did this properly, we're going to discover something useful about plane mirrors. The location of the image. If I measure from the object to the mirror, and I've got about 4.5, 6, 7, 8, I've got 4.8 centimeters, our image should be the same, and holy moly, I did it. I got a good one this year. I guarantee right now some of you are looking at your picture going, ooh, yeah, mine don't look so hot. Don't sweat about it. Any little deviation of an angle is going to bring that image in or out. Don't sweat about it, all right? When I'm marking this, say on an assignment or on a test, as long as you've done a pretty good job of measuring your angles, like if you haven't really added 5 degrees to your reflected ray, right? If you like, let's say you added 5 degrees, that's a screw up, right? But if you like kind of added like a half a degree because you were just kind of in a hurry, don't worry about it. A half a degree is enough to really shift that intersection point a lot. I'm going to check the bottom. What do we got here? I got a 3.4 centimeters. And here I got a, yeah, goodness gracious, the bottom part wasn't so good. I got a 3.7 centimeters. Ooh, not so good. Okay? All right? Questions or concerns on finding images for the plane mirrors? All right, now, whenever we do an optical diagram, we now need to describe the image. All right, and I'm going to switch back to the PowerPoint. And if I can figure out which button to push, that would make life a little easier. So we've now drawn this. We're in good shape. That's good. And don't write this all down. This describes exactly what I described to you a moment ago. When your eyes detect light, reflected light from a plane mirror, your brain projects these light rays backwards in a straight line. This results in your brain thinking that there is a light source behind the mirror, and this is where the light rays originate from. This kind of image is called a virtual image. I'll talk more about what a virtual image is. A virtual image is an image in which light does not actually come from that location. Don't worry about that. I do want you to write down this. Characteristics of an image. We are going to be locating images quite a bit in this unit. We have to talk about images that are formed by curved mirrors, and we're going to talk about images that are formed by lenses. And every time we locate or draw or find an image, we want to describe it. And we use the acronym SALT to help us remember on what we want to describe. The S stands for size. Now, when we compare images to objects, that's what we want to compare. The image to the object. So we ask ourselves, what is the size of the image compared to the object? So it's always in comparison to the object. In a moment, I'm going to go back to the piece of paper here and we will do the SALT for a plane mirror. But we can talk about it before we even get to writing it down. So for a plane mirror, what size is the image compared to the object? Always compared to the object. What's the size? Yeah, Marissa? Same. So for a plane mirror, it's the same. We're going to find when we have curved mirrors, it's not necessarily going to be the same. If you've ever looked at yourself in the back of a spoon, that's a curved reflector. Your face doesn't look the same as it does when you look in a regular mirror. So we will obviously have different answers other than the same. Attitude. Attitude describes whether the reflection is the same way up or whether they're in opposite directions. Again, when we get talking about other types of mirrors, we're going to find that we can have an image that's completely upside down or inverted compared to the object. In this case, what is it for a plane mirror? Is it right side up, the same, upright, or is it inverted? This is not a difficult question here. What is it? Megan, what is it?
Upright.
It's upright. When you look at yourself in a plane mirror in the morning, you should see yourself upright just like you are, unless you're
Not with a spoon.
not with a spoon. And we'll get to that when we get to curved reflectors. That'll be tomorrow. Location. We want to describe the location of the image with respect to the optical device. So in this case, it's the mirror itself. So we want to describe how far away the image is from the mirror. How far is an image in a plane mirror compared to the object compared to that mirror? The same distance, we'll write it down in a moment, but the same distance behind in this case as the object is in front. And we'll write that stuff down in a moment. Now, image type. There are two types of images that can exist. One is a virtual image. A virtual image is an image that, that the light doesn't actually come from that location. That's a tricky way to describe it. A second way to describe it is a virtual image cannot be projected onto a screen. And a third way to describe it, to see a virtual image, you have to look into the optical device. You have to look into a mirror to see your image. Real images are different. Real images, the light actually comes from that location in space. It can be projected onto a screen. Right now, you're looking at an image that is created by this projector's lens, and it actually can be projected on this screen. So this image you're looking at is a real image created by these lenses. You can't just do that with a mirror. You can't just take a mirror and project an image of somebody's face onto a wall. You have to actually be looking into the mirror to see their face. So for a plane mirror, it's a virtual image. We cannot project that. All right, let's go back to the piece of paper. One more time, I want to show you one more thing, and then we're going to talk about some applications of some plane mirrors. So I'm going to switch the input back. So right now, off to the side or at the bottom, my paper can't move, so I'm going to put it off to the side. You can put it wherever you want. We're going to do the salt here. So what did we say? How's our image compared to our object? Right there? Yep. Same. Attitude. Yep. Upright. Unless you had a bad morning, and if you're looking in the mirror and you're frowning, then you've got a bad attitude. Bad attitude? No? All right. I'll keep going. Jeez, guys. You guys are a tough audience. Location. Where is the image located with respect to the mirror and the object? This takes usually a sentence or two, yep?
The same distance.
Yeah, so we want to write down same distance behind mirror as object is in front. So sometimes it takes a statement to describe it. But we're describing where the image is with respect to the mirror and the object. And the type for this one is virtual. You must look into the mirror to see the image. And it cannot be projected. All right? Yep.
What an example of a real one?
An example of a real image? Well, this image right here is real. All right? I can project it onto something. Okay? And the light that is making that image is actual real light. So we've got actual real light striking the screen and then spreading out towards you, and you're seeing this real image right here. All right? We can make real images with curved mirrors. I'll show it. I'll explain to you later when we get to curved mirrors. So I can see the image by looking at it on the screen, but I can also see the image by looking at it down there, and it's really hard on your eyes, but you can see it down there too. Now I've got bright spots in my eyes. But with a virtual image, I have to be actually looking in the device to see it. Okay.